thought it was more than that. Okay, and we'll go from current slide. One final comment to make in this section. But before we do that, let me talk about some of these announcements. I think you've heard most of them until you're sick of them, so I'm not going to go over all those again. But there's a few days now going that my office hours, if they're not shot, they're changing, okay? So let me go through a little bit of that right now. Today should be fairly close to normal, whatever normal is, okay? Tomorrow, my office hours will be modified some because I do have I'm taking my afternoon class on a field trip, okay? And so normally my office hours on Tuesdays and Thursdays are 11:15 to 1:15, okay? Tomorrow, as soon as 11:15 gets here, as I get out of that class, I have to book it to the Birmingham campus to pick up a vehicle so I can take my class to the field trip. So that 11:15 till probably at least 12:15, I'll be off campus. I'll be back and forth between campuses. More than likely, it'll be closer to 12:30 because, just the paperwork and all that kind of stuff. So it takes me almost 30 minutes to get there, almost 30 minutes to get back. So that shoots an hour, and then the paperwork and that kind of stuff will probably take at least 15 more minutes. So I'm figuring I won't be back hopefully around 12:30, plus or minus one side or the other at 12:30. And then at 1:15 we leave for the field trip.
Where you going?
We're going to Channel 13 Weather Center. We just finished a little bit ago, a chapter on weather and climate. I really don't have a good lab for them to do that, so I take them to Channel 13. I know Jerry Tracy goes to the church, so he hosts us usually, and it's usually the students like it a lot. So that's their lab, their last lab. Actually, it was next to the last lab, but we couldn't schedule it until tomorrow. We should have had it last Thursday, but we couldn't get it scheduled in time. Okay, so that shoots tomorrow's, at least some of tomorrow's office hours. Now, I'll make up for that because we'll probably get back from the field trip around 4-ish or so, and I've got a few students taking the final exam then after we get back, maybe the last test and the final exam. So it'll be another 30, 45 minutes probably. That'll be occupied. But then sometime around 5-ish or so, I should be through with them. So I'll be back in the office then. Or I'll be up here doing, you can come see me. So, okay, Friday, okay. We've got to go out of town this weekend, and there's something happening Friday evening, and I don't know what time it starts. And if it starts earlier than I'm anticipating, I may have to leave campus earlier than I normally do. I usually leave at 12 or sometime after 12. Now it's not going to be any after 12. It may actually be a little before 12. So technically my office hours are 8 to 12 on Fridays, but most of the time I'm there later. This time I may have to leave a little early, depending on what time the events start. And Daniel's here. Now, one reason of difficulties with the field trip and getting transportation and stuff for it is the fact that tomorrow evening at 7 o'clock is the coronation of Miss Lawson State. And that is a pretty big deal here. I never really was involved with that kind of money when I was in college and never paid much attention to it. But it's a lot bigger deal here than it was where I went to school, I think. So it's very nicely done. And what's more, it happens right next door. They used to do it at the gym on the Birmingham West campus. Now they're doing it at the, like this year at the Civic Center, right here. And Vince is here. All right. So we're only missing Catherine and Thornton. Okay, hopefully they'll be coming. So tomorrow evening, 7 o'clock, Bessemer Civic Center, just right next door. Miss Lawson State coronation, and it is a very nice affair. Okay, but all day long they're going to be moving students around and stuff, so they got the band reserved all day. So that means we are having to use 2 cars to move students through the thing. So I've got to get a car from that campus and from this campus. So neither campus had 2 cars available, 1 each. So it's really been a pain in the neck working all this out this time. All right, so that's Friday's office hours too. Now, this week is the last week in the first mini-term. Are any of you in first mini-term courses? You are. You know about the student course evaluations for the first mini-term?
I know about them, but it was just for weight training. I still got to do one.
I imagine they got one down there, so I would say.
He told us we had our last class last week. Like we took the final
Okay, yeah, but you do this online. You really shouldn't do it in the classroom. What's that?
I think they sent it to the email, right?
Yeah, they sent you an email with a link, and that's the easiest way to get there. If you deleted the email or can't find it or something, you can go to the Lawson State webpage, and I believe you click, on the webpage, there's a bunch of blue tabs at the top of the page, but then there's one big gold tab that says Quick Links. If you click on that, and then I believe it's under Student Surveys, I believe is what it's listed on. You scroll through that, it's got lots of stuff in it, so it's not all that quick, but scroll through that till you find Student Surveys or something that means that, and then click on that, and you can get there that way. But if you can get the email, that's quickest. They give you a link, click on it, and you go to it. All right. Now, that also means that this week is the end of the first half of the term. Next week starts the second half. So we are technically at midterm over the weekend sometime, which also means that we have to do a midterm, quite often a midterm progress report. And did I give you the test? I did. Yeah. Okay. Did everybody get the first test? Okay, good. Thought I got it to everybody. Did you get the first test?
I got it.
You did. All right. Sorry I got it to you so late. I thought we would be through with chapter 5 long before now. Finally, when I saw how much we were covering in 5, I decided, no, we needed to have a test on 4 and a test on 5. So, got it to you late. If you can get it to me next week, you just got yours today, so you might not be able to. That would be great, and that way, if they do get real picky about it, I can show that there's grades out there. But if not, don't sweat it. This is a small class, upper level class. They're not as worried about you guys as they are Math 100s and 098s and that kind of stuff. So anyway. Or if you get your paper in, and one person has gotten the paper in already, not here, but has gotten the paper in. So if you get a paper in, that would give you a grade, and then, but I don't think anyone will be too concerned with it. All right. Now, let's move on. Tuesday, I have a doctor's appointment. So that shoots my office hours somewhat on Tuesday. My doctor's appointment, normally, again, they're 11:15 to 1:15. There's 2 things changing on Tuesday. One is the doctor's appointment is at 10:40, but I have to be there for labs at 9:40, which means I have to leave campus at 9. But I'm usually in class then anyway, so that's not in office hours. But with the appointment at 10:40, I can't possibly get through with the appointment, I don't think, before 11, and then maybe 45 minutes back here at the campus, 11:45. So I won't be in the office at 11:15 as normal. No sooner probably than 11:45, and maybe even later than that. But the second thing that changes is because I have a first mini-term physical science class, tomorrow is its last class, that's the field trip, and then the second mini-term physical science class starts later because the automotive students, some of them are in that one, and they don't get out of their block of classes until 3. So that means we won't be starting until 3:15, going until 7:45. So what that will do for the rest of the term is increase my office hours on Tuesdays and Thursdays from 11:15 to 3:15. So that gives me a lot more office hours on Tuesday and Thursday. Of course, it makes me here very late at night on Tuesday and Thursday, but that's okay. That's why they pay me the big bucks. I'm so happy with it. Okay. But anyway, even though I won't be in the office 11:15 on Tuesday, I'll have office hours until 3:15. And that'll be till the end of the term, 11:15 to 3:15 on Tuesday, Thursdays. So a lot more opportunity to catch me then. All right. That's all I can think of right now. Any questions on any of that stuff or on calculus stuff? Okay. Now we're in Chapter 5, Logarithmic, Exponential, and Other Transcendental Functions, and we had just done example 7, and they talked about some other stuff, and we got down to that last, a final comment, and here it is. The final comment, remember that L'Hopital's rule can be applied only to quotients leading to the indeterminate forms this or that. Okay? Now, sure, they talked about infinity minus infinity or all these other weird things, but you have to be able to express them in one of those two forms. Otherwise, it doesn't make sense. For instance, the application of L'Hopital's rule here, the limit as x goes to 0 of e to the x over x. Is that one we would use L'Hopital's rule on? Why not? As x goes to 0, what does e to x go to?
1.
1! That doesn't qualify. It has to be a 0 or infinity up there. And if it's 0 or infinity, it's got to be 1. Yeah, that goes to 0, but this goes to 1. So don't use it where it doesn't apply. And this doesn't apply there. Okay? Yeah. This is not an indeterminate form. This is a undefined form. 1 over 0 is never defined. It's never going to have a limit. Don't even try. Okay? So it's only the indeterminate forms that you would apply to L'Hopital's rule. The reason this application is incorrect is that even though the limit of the denominator is 0, the limit of the numerator is not. It's 1. And the hypothesis of L'Hopital's rule not been satisfied, so don't do it. Okay? Do not do it. All right, and is that the last slide? Yes, it is. So I think we did all the homework exercises here. I'll go over them again quickly with you. Either 3 or 5. They're both at calcchat.com. And by the way, all the answers are in the back too. But at CalcChat, you see tutorial help and worked out solutions for the problems. Any of the odds 7 through 13, they're all at CalcChat. 7's at CalcView. That gives you even more detail at CalcView, but usually none to one, only one problem will have that. Then do any of the odds 15 to 41, they're all at CalcChat. 29's at CalcView. Do any of the odds 43 to 51, no, to 61, they're all at CalcChat. 51's at CalcView. Do either 63 or 65 if you would like. These are exploring concepts. Hopefully their answers are at CalcChat as well. And here's Catherine. And here's Jordan. Ding, 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 ding. Perfect attendance today. Way to go, team. Okay. Y'all started the term perfect attendance every day, but recently it's kind of fallen apart, but it's good to see it back again. Then do 67 is at CalcChat. Either any of the odds 69 to 73, they're all at CalcChat. 75 or 77 or both, and they're both at CalcChat. Now, the next group, to think about it, you certainly are welcome to do those. I kind of don't like this kind because they're giving you something wrong and saying, try to describe the error. I don't like them to ever give you anything wrong because I'm afraid you'll say, oh, I saw that in the book somewhere. Yeah, but it was incorrect, so, but if you keep that in mind, you can do 79 or 81. They should be at CalcChat as well. 83 should be at CalcChat. 85 should be at CalcChat. And then there's a number of applied problems that you can do in either 87 or 89. They should both be at CalcChat. 89 by the way, introduces another function that you'll run into maybe in upper level courses, possibly, the gamma function. So if you chose to write a paper about that, that would be okay. Well, now that we brought that up, this one of my best classes ever, of course. Uno! Only one paper has been turned in, so please don't forget about your research papers. All right, then do either 91 or 93. They're both at Calc Chat. True, false, any of the odds 95 to 99. They should be at Calc Chat. Then there's another couple of problems. 101 should be at Calc Chat. 103 should be at Calc Chat. And then there's a few you can choose from, any of the odds 105 to 109. They should be at Calc Chat. Then for further information, they have some proofs. 111, indeterminate forms 113, finding the limit 115. You can do any of those if you choose. All right, now let's get to 5.7, where Clark wanted me to go to begin with. All right. Okay. I think 5.7 will probably just do a slideshow. Probably not, we'll see, but my tendency right now would think probably not have any of these on the test, but let's just see how they go. If there's those that are pretty necessary, it looks like, things you will run into. Okay, let's start with the inverse trigonometric, go back this slide. Inverse trigonometric functions, differentiation. That's what we're looking at in 5.7. 5.8, I think, will be integration. Let's see. We'll develop properties of the 6 inverse trigonometric functions. I really don't know why, but I guess we will. We very seldom use an inverse secant or an inverse cosecant. It's just not very useful. We'll differentiate the inverse trigonometric function and inverse trigonometric function. Review the basic differentiation rules for elementary functions. That may be worth something there. Let's see. So let's look at the inverse trigonometric function. None of the 6 basic trigonometric functions has an inverse function. Whoa. Why are we looking at them then? Well, over its whole domain. Does anyone remember why not? None of the 6 basic trig functions has an inverse function over its entire domain. Anyone remember why? Trig functions are all periodic functions. Therefore, they're not one-to-one. Okay, and you have to have a one-to-one function to have an inverse. This statement is true because all 6 trigonometric functions are periodic and are therefore not one-to-one. I didn't know they were going to say the same thing. In this section, you will examine these 6 trigonometric functions to see whether their domains can be redefined in such a way that they will have the inverse functions on the restricted domains. This, I think, should be a review when you had trig. So maybe this isn't, I thought we were going to be doing more. So under suitable restrictions, each of the trigonometric functions is one-to-one and so has an inverse function as shown in this definition. Okay? Now, here's the definition of the trig function, of the inverse of the trig function. Y is equal to arc sine, and I actually prefer sine to the minus 1. That to me is better. Arc sine would take more effort to write this, and it just seems like an archaic term to me. I would say inverse sine of x. If and only if, and that's why I have to have things, if and only if, sine of y is equal to x. Remember, inverse function undoes a function. You exchange the x's and the y's, okay? So inverse sine of x equal y means that the sine of y is equal to x, okay? That's what the meaning is. Now, and I know the book doesn't like this, but this helps me visualize, sort of realize, and think about it right. What do we take the signs of, or any trig function of? Angles, right? That's what you take a trig function of. Angle in radians or angle in degrees, right? You take it, and in calculus are almost always radians. And true, a radian is not really an angle measurement. It's a ratio of two entities, the curve, the arc length to the radius. That's what a radian is. But still, it's an angle, okay, and for all practical purposes, it's an angle. And you take trig functions of angles, producing some number, okay? The sine of pi halves, or sine of pi halves is 1, okay? Pi halves is the angle, 1 is the number, a numerical value. Sine of pi 6 is 1/2, you know. Yeah. So you put an angle in here, you get a number out here. So therefore, when you're doing an inverse sine, or any inverse trig function, that's your number, that's your angle. Okay? So that is something to keep in mind. So, if that's the case, this is your angle, that's the number. Where is the sine 1 to 1? Well, the sine, remember, repeats itself forever. It's not 1 to 1. Horizontal line test is failing miserably, okay? That's the test for a 1 to 1. But where would it work? From minus pi halves to pi halves. So therefore, that's going to be the y values here, minus pi halves to pi halves, including the endpoints. And what are the x values going from them? Minus 1 to 1. Okay? I think in terms of the trig function rather than in terms of the inverse trig function. So if you get that right, then you can get this right. Your domain then is minus 1 to 1. The range, which is the y here, is minus 5. That's your angle. Okay? Same for the cosine, except the interval. Because cosine starts at 1 and goes down to minus 1. That's your range from 0 to pi there. And you include the interval. The domain's still the same. The range shifts. Now your tangent function, remember, tangent of y is equal to x. If you were to draw that, that goes from minus pi halves to pi halves because it's not defined at minus pi halves and pi halves. So whereas here, you have the equal sign there because it is defined there. Here you can't. Those are your vertical asymptotes because that's where you're dividing by 0 because tangent is sine over cosine. Anywhere cosine is 0, you can't ever evaluate that. So tangent is only good from minus pi halves to pi halves, but it repeats itself, but it can't ever be evaluated there. So but then what's the value in there? All real numbers, the range of that. So when you're doing the arc tangent, the domain is all real numbers, but your range is limited to minus pi halves to pi halves. Okay? Arc cotangent is the same. It's just limited by it's cosine over sine. So everywhere the sine is 0, all the whole pi's in the interval pi is 0. So those are thrown out. So we limit it to 0 to pi. But it takes on all real values in between. Now this is the arc secant and arc cosecant. Why even mention it? Okay? If you remember how they look, arc secant what you do is first do your cosine function, okay? And then everywhere that cosine is 0, because secant is 1 over cosine, you have to have a vertical asymptote. And cosine is 0 at the half pi. Well, I'm through it already. Okay. Thank you. Okay. So, there's your cosine function. Starts at 1 and goes down here like this. Well, everywhere that at 0, the secant would be undefined. So the secant, at the peaks of your cosine, that's the values of the secant, but it has to stay between those zeros. And then the next one down here, the value of the cosine is the peak of the secant, and you have to stay within those zeros. So that's how it looks. So what they say then, the arcsecant, they define, well, number one, the absolute value of x is always greater than or equal to 1, but your range is 0 to pi, just like the argument for secant would be that, except y can't be pi halves because it's not defined. So that's a weird looking thing. At 0, you're at +1, okay? And then it goes like this from there. And at pi halves, okay, it's just bizarre because you got one leg of this one here and another leg down here, and they're separated, and it's just a weird thing. Who would ever use that? Same thing for arc cosecant. So I don't ever mess with those. It's just not worth trying to remember anything on it. If you run into it in your engineering, curse me. Okay, you say he should have told us this. I can't see any practical application of that. So here's how they look. There's your arc sine. Okay, if you picture a sine function that does something like this, so the arc sine is like this, inverse sine. The cosine does like this, so this does like that. Okay, it's a little weird. The arc tangent does like this, so the arc tangent does like that. The arc cotangent, why they do them like this, I don't know. The cotangent does like this, so reflect that over, and it's like this. Basically, reciprocal tangent. Not quite, but opposite. Shift it up. Here's what your arc secant looks like. Arc secant, this one. How bizarre is that? And when are you ever going to use that? Now your domain from negative infinity to -1, including -1, and then from +1 to positive infinity. And so you see you have this on there. Nothing in between and miles apart from that. And the range is 0 to pi halves, not counting pi halves and pi halves. So, no. And then arc inverse cosecant, the same thing. Now it's down here. It's just a really bizarre function. Okay. Big gap in the domain, it's strange. So I wouldn't worry with those two. Y'all need this review in trig. This is stuff we did in trig. But if you need it, we'll do it quickly if you want to. Yay or nay? Do it? Okay. Now, here's how I do these. You can do them any way you want to. How I do them is rewrite. Well, first, name an angle. Pick an angle name for it. What's your favorite angle? X? Okay, we can call it X. Now, keep in mind, X is the angle, -1/2 is obviously a number, right? Now, I want you to rewrite that mathematical equation there, but not using an inverse function.
So, sine to the -1 is the same
No,
thing.
sine of...
No, I mean, sine to the -1 is the same thing as
Yeah, this, oh, okay, yeah. You could write that like that, yeah. So write me an equation that's equivalent to this one, but just done separately, differently. just like here. Y is equal to arc sine x, if and only if sine y is equal to x, right? Okay, do the same thing for me here. Rewrite that equation with your x put in there.
Sine -1.
No? Oh, no. Okay. This is your sine, you're calling it the inverse sine. That's what I like to call it, inverse sine. Either arc sine or inverse sine. Okay? That's one way of expressing a concept. The same concept can be expressed this way without an inverse sine. That's what I'm trying to get you to do. I want you to rewrite that without using an inverse. Sine x is equal to -1/2. See, one equation does the inverse, the other does the function. And you just exchange your input and output, right? So before, your input was the -1/2. The inverse sine of -1/2 gives you your output x. Now exchange those and use the inverse of that function, which would be sine of x would give you the -1/2. You see that? Okay. Now, at this point, then you ask yourself, what angle x gives you a sine of -1/2? Keeping in mind that you have to stay between -pi-halves and pi-halves. That's the place where sine is 1 to 1. No, it's going to be fourth and first. -pi-halves to pi-halves. Sine is positive in the first quadrant. All things are positive in the first quadrant. And it's negative in the second quadrant, but think about that. Sine does like this. No, sine is positive in the second quadrant. So it can't possibly be second quadrant. This thing right here. No, okay. Third quadrant and first quadrant aren't even connected. So don't choose that. The sine is also negative in the fourth quadrant. And -pi-halves the fourth quadrant, the pi-halves the first quadrant. So that's where you go. One of those two. Now obviously this has to be in the fourth quadrant. So what angle x, when you take the sine of it, we'll get, and it's in the fourth quadrant, by the way, some negative value. Don't use 300 or something like that. That's in the fourth quadrant. No, or I should be in radians. 7/8 pi or something like that. Don't use that. Use a negative something another. So what angle x gives you when you take the sine of it, you get a -1/2. Okay?
What's the one before? It's like the one
Yeah? Help yourself. Okay.
7/6.
Okay. Except I said don't use those. Okay. 7/6 would be in the third quadrant. And that certainly would be a place where this is -1/2. But remember, we're in the fourth quadrant between -pi-halves and pi-halves. That's your allowable thing. Let's go back to this one. Well, actually, this one will work too. See, whoops. You have to be between -pi-halves and pi-halves. Yeah. That's where you're allowed to be. Whoops, wrong, and right there it shows -pi-halves to pi-halves. Where is sine? Sine of what angle is 1/2? In the first quadrant. pi/6. So in the fourth quadrant, it's -pi/6. Sine is, an odd function. So just do the same thing to the minus side. It's going to be the opposite. Okay? Draw your circles. Okay? Do it. I do it too. So this will be x equal -pi/6. Okay? Maybe we did need to go over this. Okay? Now, what you want to name the next angle? You can name the same thing if you want to, but x, okay. Let that be x. That's what we're looking for, okay? Write me a sentence that says the same thing as this, but in a different form, an equivalent statement. Cosine x equals 0. And remember now, for cosine, you're between 0 and pi. So what value of x between 0 and pi do you get a cosine equals 0? Pi over 2, x equals pi halves. Perfect. Okay? All right, you want to use x again? No! Why am I putting it? I was looking at the next problem. Sorry. Okay, you want to use x again? Okay, write me an equivalent equation for that one. What's that? Cosine is y. Cosine is usually the x. But this is not a cosine. Oh, okay. All right. Now that's why I don't like to use x as an angle, because you were talking about this x is not.
Oh, no, I was
Right, okay, yeah. Yeah, cosine is what's on the adjacent side, which is usually the horizontal, and y is usually the opposite. Yeah, so that's what I thought you were asking. That's not this x. Okay. Give me an equivalent equation for that one. C. Anybody? Tangent x is equal to square root of 3. Now, I think on this one, I want to draw me a circle too. But what I want to do is square root of 3 over what? That changes. That's a different value. I want the same value, but I want to put it over something. Over 1, exactly. And what is tangent x? What is tangent of anything? Sine over cosine. And sine, what did you call it? Y. Okay, it's y over x. Now, sine over, okay, it's y over x for, okay, let's go back. Sine is equal to y only on the unit circle when the radius is 1, okay? Because then the hypotenuse is 1. But whatever circle you have, big, small, or whatever, tangent's always y over x, because it would be y over h over x over h, and the h's go out. So the hypotenuse can be anything, but it doesn't really matter. Okay, so what I do on this one, this isn't going to be a unit circle, but this is still going to be your tangent, okay? So what we have here, your y value is going to be root 3, and your x value here is going to be 1. Okay, whoops, 1. Okay. Now, what does that make your radius? Clark almost let it cat out of the bag, because he just said it right when he threw up that other term there. Okay, the 2 part. Sine of an angle could be square root of 3 over 2, and that would be pi thirds. So the 2 is your appropriate thing. See, if this is your x, that's your y, you remember r squared is equal to x squared plus y squared. Isn't it? Cosine squared plus sine squared is equal to 1, right? So x squared plus y squared is equal to r squared. So what would be our r in this case? 3 plus 1 is 4, and square root of 4 is 2. That was your over 2. That's what I was trying to get back to. So here your radius, you're going to have a circle of radius 2. Okay? What's that? Well, you could, but it's easier to look at a 2 circle because then if you do square root of 3 over 2 over 1 over 2, yeah, that would work. Sine over cosine, that would be perfectly fine too. But, okay, either way you want to do it. They both work, okay? Now, what angle are we dealing with that your x would be here and your y would be there? Pi over 3. So the x, not this x, x equals pi thirds. Yeah. If unit circle, you see that just as well, fine. I see it better this way, but whichever. What's that? Yeah. Okay. But that's another course. Not my responsibility. Okay, now. This next one's a little bizarre. You want to make that x again? Right? What would be your equivalent statement then? Sine x 0.3. Now, that I can't give you an exact answer. Okay? You can give an approximate answer with that. You certainly can. Because all you do is do inverse sine of 3.3. That'll give you an answer. Okay, 0.42, blah, 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 right? Yeah, an approximate thing. And that's certainly correct. So if you wanted to do that, you could. X would equal, and this is in radians, 0.42, blah, 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 blah. Yeah, it goes on and on and on. Is that what you said? 17. Oh. Inverse sine of 0.3 is 0.17? Okay, wait. All right. I guess I misunderstood. What is your x in this case? You can do it right from that equation. You don't have to do the sine. This doesn't give you anything that's helpful. This one doesn't. If you're doing it on the calculator, do inverse sine of 0.3, and what does that give you? 17.45760. You said the answer was 17. Say again? Oh, you in degree mode or you in radian mode? Get out of degree mode. Yeah. Okay, that's why 17 was making no sense at all to me. Okay. Second?
0.2955.
Okay, that sounds more reasonable. Now, here's one reason I say it sounds more reasonable. Okay? I want you to picture. Oh, let's go back here. Yes, this will be a great place to do it. Notice here the sine function. Between here and there, what does that look like? Awfully close to it anyway.
Straight line?
Yes. In fact, the identity function. Y is equal to x. So for very small angles, which are measured this way, your sine and the value of sine in radians are almost identical. Okay? And same thing holds for tangent. That is almost your identity function. So if your x is in, here, in this case it would be the y in radians, and the x is the tangent value, you'll see. So therefore, it's not at all surprising to me when you do the sine of 0.3, which is a very small value, okay, you get 0.2955, which is almost 0.3, right? So you're very, very close. On small angles, the sine of a small angle is going to be very close to its radian. The sine of a small angle in radians is going to be is very close to the value of that sine. Okay? because sines and tangents on small angles are almost on the identity function. Not quite, but close to it. Okay. They do have at the bottom of the page 372 exploration of the inverse secant function. It's just totally bizarre. I'm not even going to mess with it. Okay. So we just did example 1. Let's see how they did it. I think I do know, and it sort of aggravates me when I see it, but let's see how they do it. By definition, y is equal to, so they use y. We used x, okay? Y is equal to arc sine of -1 implies that sine y is equal to -1/2, okay? In the interval, negative pi halves to pi halves, the correct value of y is minus pi 6. Because where is it? Negative pi. But if it's 1/2 at pi 6, it's going to be -1/2 at minus pi 6. Okay? So arc cosine of -1, or arc sine of -1. Second? Yeah, that's what this says. You have to be between the fourth and the first quadrant. Minus pi halves to pi halves. That's where it's defined because the sign does like this. If that's the origin, the fourth quadrant is -1. First quadrant at pi halves is +1. So you have to be in that. Now, the second one, by definition, y is equal to that, would imply that cosine y is equal to 0. And where does that happen? In the interval 0 to pi, because cosine, for it to be 1 to 1, it's at 0 down to pi. It never backs up on itself there. You couldn't be back here because then horizontal line test fails. You can be over here 0 to pi, and that would be at pi halves because that's where it crosses the x-axis. So, arc cosine of 0 is, by definition, exactly 1 pi halves. Okay? And, excuse me, y is equal to arc tangent of 3, square root of 3, implies that tangent of y is equal to square root of 3. In the interval minus pi halves to pi halves, this is incorrect. Does anyone see what's incorrect about it? You can't have minus pi halves or pi halves. Those should be parentheses. For tangent, parentheses. You can't take the tangent of minus pi halves. It's undefined. Pi halves is undefined. So there you have to be parentheses. Okay? But their meaning is the same. Where does that happen? Like you said before, pi thirds. Okay? Let's see if they got that wrong in the book. Sorry. Goodness. No, in the book they got it right. Okay? They have parentheses around that. The graphics guy got it wrong. Okay? So arc tangent of root 3 is pi thirds. And using a calculator set in radian mode, and someone gave me a wrong answer, didn't they? Mm-hmm. What's that? So they may, let me look in the book. Well, they said it there too. Let me see. Okay, you're in radian mode, aren't you? Oh, you did sine. It's arc sine.
Oh.
Yeah, you do second. Okay. Yeah. How do I? Is on what change? Okay. You do shift sine. See, that gives you the inverse sine of 0.3. That's what they're asking for. Close parentheses equal 0.305. Yeah. Yeah, no problem. But I knew it was close either way. So 0.305. All right. Okay. Inverse functions have the properties. This is for all inverse functions, not just sine the trig functions. The f operating on f inverse is equal to x, as long as x is in the domain of f inverse. Okay. Otherwise, it doesn't make any sense. Okay. And f inverse of f of x is equal to x2, but now the x has to be in the domain of f. Okay. So that's the only little trick here. These statements are both true, but the x's may live in different places. This is in the domain of f inverse. That's in the domain of f. When applying these properties to inverse trigonometric functions, remember that trig functions have inverse functions only in restricted domains, so that's why it's important for these. For x values outside those domains, the two properties do not hold. Okay. For example, the arc sine of pi is not equal to pi. And the reason is pi is not in the, it's in the domain of sine, but it's not in the range of arc sine. So they sort of set things a little backward. Tells what's the sine of pi? 0. And the inverse sine of 0 is 0, not pi. Okay? Because inverse sine can't have a domain, a range outside of minus pi halves to pi halves. Okay. So that's why that property doesn't hold if you're outside either the domain or the range, okay, depending on where you're dealing with. So here are these inverse properties, okay, properties of inverse trigonometric functions. If x is between minus 1 and 1, and your y is between minus pi halves and pi halves, including, all those are less than or equal to. Then the sine of the inverse sine of x is x, okay? Because you can take the inverse sine of anything between. Remember, take inverse sines of numbers to give you angles. Those are your angles. These are your numbers. That's equal to x there, and inverse sine of y, arc sine of sine of y is equal to y if the y, because you only take sines of angles. So that defines this. So you see these properties hold to take a sine of an arc sine, you get the same thing you put in if you're within the right range, domain, whatever. And same thing here. If you're in this domain, then the arc sine of sine y is equal to y. If you're outside of that, you can't do it. Okay? And for arctangent here, notice that they don't give you an x. X can be all real numbers, okay? And y, though, has to be between minus pi halves and pi halves without the equal sign, okay? Because you cannot take the tangent of negative pi halves or pi halves. They're undefined. That's your vertical asymptote, not defined there. Okay, so as long as you're between those, but not including the endpoints, then the tangent of arctangent of x is equal to x for all real numbers. That works. But going the other way, arctangent of tan y is equal to y only if y is in this range. Okay? Now, don't even mess with these two. They didn't even do cotangent, which is far more useful than secant and arcsecant and arccosecant. Well, they didn't do arccosecant either. I don't even want to mess with that. They should have done arc cosine. That makes sense, okay? Inverse cosine makes sense. Inverse tangent, inverse sine. Even inverse cotangent is okay. But secant and cosecant, they're just such weird functions. Don't even mess with it. All right. Now, can we solve that equation? What would be your first step? what would be your first step? It's an easy first step. One we've practiced several times this morning already. Second? I can't hear. Sorry.
Assign a number, that number, the 11 for the arctangent part, or we write it too much?
Say that again.
Rewriting it.
Yes, rewrite it. How would you rewrite it? Tangent of
2x.
Okay. Yeah. Again, if you have an arctangent function, then think, that's your angle, this is the number. Okay? So when you rewrite it, you can only take tangent or any trig function of an angle. And what was the angle up there? Pi fourths. So it's tangent of pi fourths is equal to 2x minus 3. Perfect. Okay. Now, what is a tangent of pi fourths? Oh boy. Who do you have for trig? I have to contact them. What is tangent of pi fourths? It's 1. Yes. Okay. Because remember, pi fourths is a 45-degree angle, right? That's your identity function. Okay. So it's 1. Okay. The ratio, the slope of it is 1. Okay. So 1 is equal to 2x minus 3. I think we can do that, can't we? How? Second? Okay. How do you do that? Second? Plus, okay, I can't hear. Add 3 to both sides, and that gives you 4 is equal to 2x, and then by 2, right? Okay, and that gives you x equal to. That wasn't that bad, was it? Whenever you're dealing with inverse trig functions, just about always, an equation with them, always write it as a trig function equation. The equivalent equation with the regular function, not the inverse function. Okay? Let's see what's next. Let me erase this so you can see how they did it. And lo and behold, okay, this works too. They take the tangent of both sides of the equation, and the tangent of an arctangent just gives you what's left, and that, which is the same as write the equivalent equation, which is a lot easier in my book. The tangent of pi fourths is equal to, undo that. Okay. And that gives you the same thing as this. Oh, and they went on and evaluated what tangent of pi fourths is, and then that gave us x equal to. Yes. All right. Any questions? All right. Now they're skipping example 3. If you want it done, we can probably do it. What you think? Is that worth? Let's do it, you said? Okay. Let's go back and do it then. Do it to it. All right. Given that y is equal to the arcsine of x, I hate arcsines. Okay, oh, they don't put parentheses, I don't know. Just seems like to me all those letters in a row, but I guess if you leave a space it makes it obvious. Okay? If that's all you're given, where 0 is less than or equal to y is less than or equal to pi halves. Okay, is that okay with you? Okay. Number 1, I always ask myself, what's the angle, what's the number? You answer it. which is the angle, which is the number between x and y?
Y is the angle and x is the number.
Y is the what?
Y is the angle.
Angle and x is the number, yeah, because the inverse function, you take the inverse scientific function of the number to give you the angle, okay? And are those legitimate angles for sine? 0 to pi halves. Sure. It's not the whole domain, but at least it's an acceptable domain, okay? If that had been pi halves and 3 halves pi, no. You're on the downside. You want to be between 0 and pi halves, and there you negative pi halves and pi halves, there you certainly are. Okay? Now, given that, it says find cosine x. Now, does that even make, oh, no, it doesn't. Cosine y. Okay? Now, I was starting to ask, does that even make sense? What did you say the angle was?
Y.
Y. Yes, it makes sense to take the cosine of an angle. Okay? So, how do we do that?
Rewrite.
All right, that sounds like a capital idea. And why would that rewrite?
Sine of y.
Second?
Sine of y.
Sine of y is equal to x. Perfect. Now what? Now, there's a little kind of a hint here. It says using right triangles. If you can imagine, that's a right angle there, okay? And let's just imagine our axis is here, okay? Now, this is your angle, y, and this is your, okay? I need that to be in a ratio. What could be on the bottom? 1. All right, good. So now we have, and this should please Jordan no end, because we're back on a unit circle, aren't we? Because the sine is opposite. So that's not the x of the x-axis, that's your x that they gave you in the problem, over your hypotenuse, which is 1. Unit circle, 1. Okay? Now, with that in mind, what is cosine of that angle? It would be your adjacent side over 1. There's nothing there. Can we get something there? Second? Yes, Pythagorean theorem. How does it go? Okay, which one you want to call A and B and C? Second? C is the hypotenuse, so we'll call that C. A is adjacent? Okay, so we're looking for A, and this is your O. Okay? I'm all in favor of that. Or, no, you called that B, didn't you? Okay. Opposite will be B. Okay? Now, we need to know what that side is. And didn't you just say that A squared plus B squared, but B squared would be x squared is equal to 1 squared, which is 1. So what's your A? Okay. A squared would be 1 minus x squared, right? Subtract x squared from both sides. So the A would be if A squared is 1 minus x squared, what would A be? It's what? New rules for taking roots, huh? Can't invent anything in here. This is not an invention class. How do you undo a square? Square root of 1 minus x squared. Now, most of the time when we take the square root of both sides of an equation, you have to put a plus or minus here. But in this case, we're only in the first quadrant. Remember, y is between 0 and pi halves. You're only in the first quadrant, so your A here can only be positive. So you don't need the plus or minus here. So just do the plus. Okay? Now, can you tell me what cosine is? That's what they're asking for. Cosine y would then be, if this A is the square root of 1 minus x squared, what is cosine y? The definition of cosine y is what? And what's your adjacent? Square root of 1 minus x squared over 1. There it is, right there. Right?
Was the 1 given?
It said that sine y was equal to x, or y'all told me that, rewriting this thing. So I need it as a ratio, so I put it over 1. Because x is x over 1. And I thought you wanted it on the unit circle, so I did it just for you. Okay. All right. Okay. All right. There is a B part to that one. You want to see it also? Yes. Okay. B part says, given that y is equal to, oh, gag, the arc secant, I said I wasn't going to do any of these, over root 5 over 2, okay, find tan y. Okay, and again, does the question make sense? Which is the angle, which is the number? The angle's y. So now tan y does make sense. Okay? Now, the other question is, can you even take the arc secant of root 5 over 2? What can you tell me? Yeah, as you know, what is root 5? Just approximately. Something greater than what? 2, okay? So you have something greater than 2 over 2, so that number, the thing in there, the number part is greater than 1, right? And you can only take arc secants of things greater than 1. Remember, sine and cosine are between minus 1 and 1, secant and cosecant are outside that, greater than plus 1 or less than minus 1, okay? So, yeah, that part makes sense too. Now we draw a picture. Okay, and sorry about this one, but what is arc secant? Okay, how do okay, let's take this and rewrite this as also secant y is equal to what? Root 5 over 2. Now this one, you're sort of set. And it's going to be awkward, but we can do it. Okay? What is secant in terms of, okay, 1 over cosine. So that would imply that cosine y would be what? 2 over square root of 5. Okay, and then what is a cosine? What's that? You can, but let's just leave it there for now. It's not hurting anything, is it? Yes, exactly. So the adjacent would be 2, that's your x value, and the hypotenuse is something a little bit longer than 2, square root of 5. A little bit, right. So we'll do 1, 2 with a little bit more, 1, 2 with a little bit, whoop, too much more, a little bit more, 1, 2 with a little bit more. Okay, so your circle is something like that. That's a pretty ugly circle, okay? Now, your adjacent is 2, so here is the angle we're talking about. This little angle right there. That is your y. And this is Yeah, this is square root of 5, and this is 2. Yeah. Okay. Say again? I can't hear you. Yes, Pythagorean theorem. And how does that work here? 2 squared. Okay, you're going to call that b. 2 squared plus b squared is equal to square root of 5 squared. Okay, 2 squared is 4 plus b squared is equal to, and what's square root of 5 squared? 5. So b squared is equal to 1. So b is equal to 1. Okay, and so this is a 1 right there. And look at that. It's almost like my picture. Okay. Ooh, okay. So what would tan y be then? 1 over 2. You got it. That's it. That's pretty good, isn't it? 1 over 2. And that's what they got. All right. Now let's see. Their drawing, oh no, yeah, their drawing is not bad. I was looking at the other drawing. All right, I think we're through with those now, okay? Now let's look at derivatives of inverse trigonometric functions. I know, I don't even want to mess with it. The derivative of the transcendental function f of x equals log x is the algebraic function what? What's the derivative of log x? What's f prime of log x? Oh man, we were doing these. What's the derivative of log x? Okay, the inverse of log x is e. What's the derivative of log x? Oh man, what was it, a week ago? Yeah, that's a long time ago. What's the derivative of log x? Please. Yeah. Huh? Derivative of log x. Not x. Derivative of 1/2 x squared would be x. What's derivative of log x? We were doing them all over the place last week. Derivative of log x is 1 over x. Remember? Yeah, okay. You'll now see that the derivatives of the inverse functions are also algebraic. Okay? Inverse trigonometric functions. Even though inverse trigonometric functions are themselves transcendental. They were really big on this transcendental stuff. I think he must meditate on it. No, I'm just kidding. Okay. All right. So derivative of arc sine is of u. Now, if they had put an x in there, it'd just be 1 over. But they put a u in there, so it's u prime over 1 minus square root of 1 minus u squared. And for arc cosine, it's a minus 1 or u prime over 1 square root of 1 minus u squared. If those were x's there, that'd be an x squared. Arc tangent would be, if that was x, it would be just 1 over 1 plus x squared with u, it's u prime over 1 plus u squared. And arc cosine, arc cotangent would be a negative of that. Okay. Arc secant is this mess, and arc cosecant is the minus of that mess. So you see, those are derivatives act a lot like your other, only with the minus sign. The derivative of an inverse trig function and the derivative of the inverse of its cofunction only differ by a minus sign. Okay, that's the key here. Everything else is the same. Now, do I sit down and memorize these? No. Okay. I tell you what I do though, because sines and cosines follow that Pythagorean identity that sine squared plus cosine squared equal 1. If we were trying to get a sine, it's the square root of 1 minus cosine squared. And that's sort of what the denominator looks like here. It's not the same, but I need to remember sines and cosines have that in the denominator. But because tangent squared is equal to 1 plus secant squared, it has the 1 plus u squared down here. Now, that's not a secant squared, but I remember it that way. Okay? Now, and because a secant squared is a tangent squared minus 1, it's back inside of the radical again. You know, because secant would be square root of that. Okay. So, but then I can't think of any reason for that to be there. It just is. So that's how I remember. That's just how my mind works. It's a little bizarre, but it does. But you know what? I'll look it up if I need to know it. You know, because I don't commit these to memory at all. Okay? So easy to look up if you need to. Okay? Now, do you want to do some of those just for the fun of doing? As in example 4. Yeah? Okay. So let's go back. For inverse sine, remember, it's u prime over the square root of 1 minus u prime. So, I swear, I thought they were going to have us do them. They're just showing us the answer. That to me is not very instructive, but let's break it out. The derivative of this is 2, and the denominator is the square root of 1 minus this thing squared. So, seemed like we should have come up with that, you know. But derivative of this is 2, and 1 minus that thing squared. Square root of 1 minus that thing squared. Which, you can do that, and that would be 2 over the square root of 1 minus 4x squared. There's not much else you can do with that. So I guess you take it one more step. Is 2 over the square root of 1 minus 4x squared. That's not very exciting, is it? So let's do this one. What would be the derivative of arctangent? 3x. 3
over 1 plus 3x squared.
Yep, that's it. And that would be 3 over
1 plus 9x
squared. 9x squared. The x is squared too.
Oh, okay.
Got it. Okay. Square the 3, square the 9. Okay. The 3x squared is in parentheses. The 3x in parentheses. 9x squared, there's no parentheses. Okay. This is really enlightening. What is this one? It's a mess, is what it is. What's that? Well, 1/2 x to the minus 1/2 is what we're going to say. Yeah. So that would have a square root of x in the denominator. So 1/2, yeah, that's what we get up there. Okay. What's in the denominator? Okay, this would be the absolute value of u, which would be just square root of x. Because the square root is going to be positive, so you don't have to do the absolute value. So square root of ooh. I'm not sure that's correct. Okay. Oh, I'm sorry. I'm reading that as secant. That's a sine. So yeah, the numerator's that, and then it's 1 minus that thing squared, which is square root of 1 minus x. Okay. I'm sorry. I was reading this as a secant.
The derivative is on top.
Yeah, derivative of what's in here is on top. Now, what I would do with that then, the next step, is take this downstairs and lose that, and then you can multiply those things together if you wanted to. And I think that's probably, in fact, bring the 2 down here too. Only thing left on the top is a 1. That's what I'm talking about. What's that?
How did they get the negative exponent?
Because you're taking derivative. Okay. All right, good question. I would write this rather than square root of x as x to the 1/2. Right? Isn't that the same thing? You don't even need the parentheses there now that I think about it. Okay? And how do you take the derivative of x to the 1/2? Say that again? Yeah. 1/2 times 1, which is 1/2. That's where that came from. Times x to the...
Oh, you got to
subtract 1 from it, exactly. So that's where the negative 1/2 comes from. So this would be 1, that's all you got up there. You got the 2 down here, that's from the 1/2. The square root of x down there, once you move it downstairs, and this is square root of 1 minus x. Well, you can rewrite that as 1 over 2 times the square root of x minus x squared. What's that? Okay, because this is 1 over 2, right? And this is 1 over x to the 1/2, right? Anything to a negative exponent, move it upstairs and downstairs and lose the minus sign, right? Yeah. Okay. So that, and when you multiply 2 things with the same degree, you can put them both in the radical and multiply them there. So that, to me, is the answer. Okay? And let's see what they did. Whoa, they right on top of mine or underneath mine or something like that. Let me clear mine out of the way. Yeah. And do they take another step? Yeah. So did I have it backwards? I think I did. I wrote it backwards. Sorry about that. It's x minus x squared. Okay. Now let's do, I think this is what I was looking at, thinking it was going to be something else. Okay, how would we do that?
I'm sorry, can you go back to the last problem? You said when you move the half, the negative half exponent down.
Okay.
What you did with the exponent when you moved it down? I know you took it
Okay.
sideways.
When you move it from upstairs to downstairs, lose the minus sign.
Oh, yeah.
Yeah.
But where is it? What you use it on?
It disappeared when you move it like that. If this was a minus out front, that doesn't disappear. But the exponent, when you move it downstairs, you lose the negative sign. Or if that had been an x to the minus 1/2 down there, move it upstairs, and it becomes x to the 1/2. Okay. You change signs of the exponent when you go across the
I get that. I'm saying, where is it?
Okay. Well, x to the, move it down here is x to the 1/2. And what is x to the 1/2? That is square root of x. So you went here, change that to x to the 1/2 to take its derivative, and then when you moved it back downstairs, you change back from exponential notation to radical notation. And then you multiply, since these are both the same roots, you can multiply what's inside. Since the roots are multiplied, you can just do the root of the product of these, the x minus x. Okay. Now we're ready for this one, I hope. Okay? Where would you begin?
Take a derivative of
Of e to the 2x, and what would that be?
2e
To the 2e to the 2x is the numerator. What goes in the denominator?
absolute value of e to the 2x.
Yeah, but e to the 2x is always positive, so you don't need the absolute value sign.
And then square root of e to the 2x squared minus 1.
E to the 2x squared. And what is e to the 2x squared?
E to the 4x.
Yes, e to the 4x. So this would become, I'm going to write it down here, hoping they're going right over there. 2e to the 2x over e to the 2x times the square root of e to the 4x minus 1. Okay. Now, notice here, this e to the 2x and that e to the 2x divide out, right? So that leaves us with 2 over the square root of e to the 4x minus 1. Now, I don't think that's a perfect square, so let's just leave it just like that. Let's see what they did. All right? Yep, they just wrote that answer down without telling you how they got there, but yeah, that's how you did it. 2 over...
You always put that up under the square root. How do you find it out? I ain't get the round the formulas down. Like how you know you gotta put it to the 2x up under the square root?
How do you know what to put under there?
Yeah.
Is that what you're asking? Okay. If you look at the rules right above that, you don't have a book with you. Okay. All right. Let's go to this. All right. Here's the derivative of arcsecant u. Whatever the derivative of u is, that's up here. The absolute value of u is there, and then this is always u squared minus 1. The square root of u squared minus 1. Which, you know, most of the time, I'm not taking derivatives of inverse secants. Okay, I don't even like inverse secants. So why would I want to know its derivative? I don't know. Doesn't matter what I like. But notice, and this is just an interesting thing, the derivatives of your inverse trig functions without the co's in front of them are all positive. The ones with the co's in front of them are all negative. I don't know.
You said the ones with what?
The inverse trig functions without co's in them, they're positive. The inverse trig function with the cosine, cotangent, and cosecant are all negative. Don't know why especially. I'll give you sort of a little hint. Somewhere way back here. There it was. Notice here, the inverse sine function is always positive. Inverse cosine function is negative. Inverse tangent function is increasing. Inverse sine function is increasing. Inverse cosine function is decreasing. Inverse tangent function increasing. Inverse cotangent function decreasing. Inverse secant function increasing. Inverse cosine function decreasing. Derivative is the slope of the tangent line. All those slopes are positive for sine, tangent, and secant, even though that's weird. And for cosine, cosine, tangent, and cosecant, the derivatives are all negative. So that's why the sign changes like that. But it's just something interesting to note. Okay, I haven't been keeping up with time. Are we out? Close to it. Okay. See if we can get a little bit more before we go. All right, that's where we left off. That was example 4. Let's see if they show example 5. I was trying to leave it up there, and now we're right over it again, under it. The absolute value sign is not necessary because sine of e to the 2x, e to the anything is always positive. Okay. Now they skipped example 5, 6, 7, and went to review of basic differentiation rules. Do you need to do 5, 6, or 7? Up to you. You want to see 5 done? You don't probably have time to do it, but you want to start there next time or not?
Yes.
You do. You want to see those. So we'll start there. Yes. Hey. Oh, here, I'll just give you my key. I'll pick up the key sometime before I get in my office, because I can't get in my office without it. So I'll come down and get it. Okay. All right. So we'll pick up then with example 5. Okay, and we'll go on from there. Let me give you the homework exercises then. We almost finished 5-7. You can do number 5 is at calcchat.com. You can do any of the odds 7 through 13. They're all at CalcChat. 7's at CalcView. You can do either 15 or 17 or both. They're both at CalcChat. You can do any of the odds 19 to 23. They're all at CalcChat. 21's at CalcView. You can do either 25 or 27 or both. They're both at CalcChat. 25's at CalcView. You can do any of the odds 29 to 35. They're all at CalcChat. And either 37 or 39, they're both at CalcChat. 37's at CalcView. Any of the odds 41 to 55, they're all at CalcChat. 43's at CalcView. Any of the odds 57 to 61, they're all at CalcChat. 57's at CalcView. Either 63 or 65, they're both at CalcChat. Either 67 or 69, they're both at CalcChat. 67's at CalcView. Any of either 71 or 73, they're both at CalcChat. And then you can do 75 if you'd like. And then exploring concepts or 77 and or 79. All those should be at CalcChat if you look into it. There's one identity, 81, or it's actually 2, A and B. There should be at CalcChat. And then there's a couple true false, 83 and 85. They should be at CalcChat. All right, there's a couple of applied problems. Any of the odds 87 through 91 are applied problems. 93 is a proof. You can do that if you'd like. It should be at CalcChat. Describing a graph is at 95. It should be at CalcChat. Maximizing an angle is 97. 99 is a proof. It's up to you whether you do that or not. All right. Thanks, man.
Get started next week.
What's that?
Oh, yeah. Wants to get started next week. So
yeah. Get it set up. Yeah. All right. Good deal. We'll pick up then on Tuesday. Wait, no. Monday. Say again?
Yes, sir.
Okay. Is that what you were saying?
Yes.
Okay. Okay. See you Monday. Have a good weekend. Of course, working calculus problems will make it good, won't it? Yeah. All right.
Exercise the brain.
Yes.